Hello, how are you? I hope that you are able to solve the assignments given so far, and you are also able to follow my lectures. What I would do that I would just go back to the assignments which have been released already, and I shall go to some of the selected problems from the assignments and just give some bit of clarifications based on the queries I am receiving in the discussion forum. So, and as you go through my live session now, whatever queries or whatever doubts you are encountering, you please write to me so that I can right away clarify those doubts to the extent possible. So, let me first go to assignment number 6. And in this assignment, there were some problems based on the separation systems. In this, as you see that in question 1, it was asked that which are the direct contact type separation processes, and some processes were named. And as you know that there are separation processes which need two phases, and when we have two phases like vapor liquid, vapor solid or liquid solid, in that case what we find that sometimes we need to mix up the two phases together, and that is what is meant by direct contact. And if there is any kind of barrier between the two phases, we call it indirect contact. So in among the various options given to you, I want this slide please to be shown. So you see that in this assignment there are four options were given to you for this to know that which are direct contact type: distillation, membrane separation, absorption, adsorption. And in the distillation process, what we do that we contact one liquid phase and one vapor phase together, so that during a mixing between the two phases, the various species can redistribute themselves between the two phases. The more volatile component will go to the vapor phase preferentially, and the less volatile components will try to stay back in the liquid phase preferentially. Similarly, in case of absorption, what we are doing that we are trying to dissolve some soluble components from a mixture, so that we can separate out some the components of a mixture. So that is based on basically solubility of the various species, whereas in distillation it is based on the volatility. And in adsorption, a solute will come out of a mixture. Again, if the mixture is in contact with a solid, the solid is the adsorbent, so the mixture has to be in direct contact with the adsorbent. So, and the species will come out from the mixture and they will get adhered or attached with the adsorbent depending on their affinity towards the adsorbent. So, this way distillation, absorption, adsorption belong to the direct contact type separation processes, whereas in case of membrane, what is generally done that there is this semi-permeable barrier which allows selectively some of the components to pass through it, and some of them are not allowed to pass and they are retained, so that on the product side, whatever components we are getting, those are not coming in direct contact with the feed side fluid mixture. So that way the membrane is the one which is a indirect type separation process. Then I go to, excuse me, I want the slide to be shown on the screen please. You see that there is a problem on the relative volatility of this vaporization. In this case, what we find that the relative volatility of a mixture A and B is given here, and the equilibrium vaporization of B is given here, and you have been asked to find out alpha BA. Now you see that we learned that in this that alpha AB, going by the definition of the relative volatility, if you see alpha AB, that is the ratio of the equilibrium constants of A and B. So alpha AB is the alpha, that is Ka by Kb, and then alpha Ba is the reciprocal of alpha AB. That means what? That in this particular question, the value of the Kb which was given to you is not really needed. Okay, so this is an extra information which was given to you. You can find out alpha Ba based on the value of alpha Ab only, and that is how you are able to get the value of Ba as 0.4. Similar fashion, you have this next question alpha on this relative volatility again, and perhaps in this particular case you have been asked to find out the concentration, and the volatility is given like this, and it's a equimolar vapor mixture, so that the mole fractions are the same for both the components, and you are required to find out the liquid, in the liquid the mole fraction of the component B. And as you see that we have gone by the basic definition of the relative volatility, and then we plug in the various values and we replace that xb in terms of xa from the summation equation, like xb plus xa equal to 1. So xb equal to 1 minus xa. So all these things we do, and we simply plug in the various values in this particular expression, and we find the value of the mole fraction of the component B in the liquid. So I hope that these are fairly simple problems, just which need some basic definitions to be remembered, and if you know those definitions, you should be able to solve these problems very easily without any difficulty. Next question also pertains to the relative volatility. In this case, three components were given, A, B and C, and in these three components you were given the relative volatilities for two pairs, like AB pair and CB pair, and you were asked to find out the relative volatility for the third pair, that is AC or CA. Okay, so it is CA. That means we again go back to the basic definition of the relative volatilities, and if you see that here we are putting the alpha AB and alpha CB, and then you know that mathematically also you can see that alpha CA equal to Kc by Ka. So what we are doing, we are writing Kc by Ka as equal to Kc by Kb into Kb by Ka. Okay, so Kc by Kb, you can see that this is alpha Cb, and Kb by Ka is nothing but the reciprocal of alpha Ab. Okay, so with these two things we can see that how we can find out the values of the value of the alpha Ca. Okay, so it is also quite simple. Next, we come to another problem that is pertaining to the assessment that whether a given mixture or a solution is at its bubble point or dew point or outside these ranges. So for that we have been given some overall composition of the mixture, and it has been told to you that this is, take it to be ideal, and then the equilibrium constants have been given like this. So and total pressure has been mentioned, and you were asked that you have to figure out that whether solution, at what condition the solution is. So in this particular problem you have to go back to the lectures and see that there were some conditions given based on the value of the Ki and Xi and Yi. So what we do, that we take sometimes we consider these particular mole fractions given in the question as Xi, and sometimes the same mole fractions we also take them as Yi, because we do not know, we have to figure out that in which state they are. So these mole fractions, once we take them as the mole fractions in the liquid phase, and another time we take them as the mole fractions in the vapor phase, and once you do that, then you come to this particular table, and in this table that you find out the values of this Ki, Xi and Yi by Ki. Then by looking at these values, okay, the summation of this Ki xi and summation of yi by Ki, what you find that this is satisfying this particular condition. So we find both these summations are coming out to be more than 1, and that is why if you go refer to the table I gave you in the lecture, you will find that this particular mixture, given mixture at the given condition is nothing but it's above its bubble point. That is above its bubble point means it is a subcooled liquid. Okay, so it is a subcooled liquid. Now, but then we come to something to do with water content. These are something which you can simply look at your lecture and you have the points over there. I am not going to this, and now I go to another problem which is asking you to find or convert. This is very important that you should know the conversion of the parts per million into the mole. Here it is asked that milligram per meter cube at some temperature pressure given. So this is very important, and this kind of problems you come up in day-to-day life also, especially when we talk of in terms of the various types of pollutants which are there in the air. Many times we put them in terms of ppm or sometimes ppb, that is the part per billion. So it is always have to have a better feel of it. We sometimes put them in terms, want to know in terms of their mass fraction, like how much mass concentration, that is how much mass is contained per unit volume of the mixture. So that in that context this problem was asked, even if the problem pertains to natural gas. So here it is for the carbon dioxide in air, and this is how you are finding this particular formula. You have to remember that this ppmv equal to mp by RT, and this gives, if you put the various values in these units, you will get this milligram species per unit cubic meter of the mixture. So one has to be very careful about the units. Okay. So you see that these are the units we have used, that temperature we have converted to Kelvin, the pressure we have converted to kilopascal, and the molecular weight is in terms of kilogram per kilomole, and this is the kind, this is the equation we get, and then plugging in the values you get it easily, the value of the ppm. You can convert ppm to milligram per cubic meter, again I am skipping the other problems. I am going directly to the problem, this another problem that is based on the adsorption capacity, and what is that asked that you have been given the BET isotherm, what you have been asked that some amount 12 cubic meter of oxygen is to be separated by adsorption using silica gel at this 30 kilopascal pressure and 90.1 Kelvin. So at this particular pressure temperature, we have to adsorb this oxygen, and oxygen is available at this particular temperature, and at the saturation, that is the vapor pressure of oxygen at this particular temperature is this value 100.4 kilopascal. Now what is asked that you have to find out that how much oxygen can be taken up by the silica gel, and this here you have been given one hint that use the BET isotherm, and this particular table is there in which you will find the various coefficients which are there for the BET isotherm. So using these coefficient values you will find that you will first have to locate this oxygen. You see that in this first column you have the various types of the adsorbents. In the second column you have the various types of gases. So as per this problem you first locate the silica gel, and then you find that it is oxygen. So you go to oxygen, and then you see that these values have been given for 90.1 Kelvin. So this also corresponds to the value given in our problem. Okay. So these two values we are finding they are right. Now after ascertaining that we have chosen the right adsorbent, the right type of solute and the right temperature, then we just simply go to the various parameter values needed for the application of the BET isotherm, and we take these values, and this is the BET isotherm equation here. So we have been given the value of the saturated pressure in the question itself, and rest of the values like Vm, Z, etc. they can be found out from our this particular table, and this Z value has been calculated based on the value of the theta A. So, from the theta A we take this formula to get the value of Z and then plug in the values over in this particular equation, and that is how we are getting this. V is the volume of the gas, that is oxygen in this case, per unit volume. This Ma is the mass of the adsorbent. So, we are getting the value of the amount of, that is the volume of oxygen that can be adsorbed per unit mass of the adsorbent. Okay. And then what we rest of the things do, that we get this particular value, that total mass, how much the total mass that can be obtained, that this is the 12, that is the, we have been asked in the question that 12 cubic meter of oxygen has to be adsorbed. So, from this value of V by Ma, I can find out the value of the Ma. So, what you find that these are some approximate calculations, and there might be some differences in the final values you obtain depending on how many significant digits you considered in calculating these values. So, what I would suggest you, if you find in your assignment that the values obtained by you is not exactly matching with the values which have been given in the problems, in that case please feel free to choose the value which is nearest to the option given in the assignment. Okay? So, do not panic, do not think that you are wrong, just you choose the value which is nearest to the value you obtained obtained and with the to the value which is given in the assignment. Okay? So, that way you solve these problems. Okay, so, this is a brief recapitulation of the problems of assignment 6, and then what we do, we go to I will go back, I will go to assignment 5 now. Okay. Now, in this also we find that here we have this assignment 5, and in this first problem I am not again going to, this first problem is all about going back to a lecture and figure out the right condition. So, you can put it, and the second condition it is about the relative volatility, whether it depends on pressure or not. This you have to see that you have been asked that for those systems which obey the Raoult's law, whether the relative volatility is independent or dependent on these things. First thing you have to understand that whenever we talk of Raoult's law, it means that these are ideal solutions, ideal gas mixture, ideal liquid solution. Okay. So, in those cases what we found in our lecture, that the value of the equilibrium constant is the ratio of the vapor pressure of the particular component to the total pressure. With this definition, we can see that if we want to find out the relative volatility, it becomes simply the ratios of the two vapor pressures. So, in this vapor pressure, as you know, the vapor pressure is a function of the temperature. Okay. However, the pressure is not appearing directly here. So, you can say that these alpha ij for those mixtures, vapor liquid mixtures which obey the Raoult's law, is independent of the total pressure of the system. On the other hand, the temperature dependency comes through the values of the vapor pressure. Then we come to some other next question, that is about the flash vaporization. I am not going into detail of these options, just to again just give you a hint that flash vaporization is done when you want to separate some volatile components from a liquid. Okay. So, what you do, that you flash the liquid either by exposing it to a lower pressure or by heating it partially, so that you generate a vapor phase from the liquid phase, and by doing so you are enabling the more volatile components to go into the vapor phase. Okay. So, that is why you are putting this flash, for separating out the more volatile component from a liquid mixture. In next, the question was on the distillation column, whether how to count the number of stages when there is a partial reboiler or partial condenser or total reboiler, total condenser. In this case also, please understand that partial reboiler or partial condenser, they cause partial vaporization or liquefaction of the liquid or the vapor, as the case may be. So when you are partially doing it, it becomes something like the flash or the partial condensation we studied, and we found that ideally a flash or a partial condensation will lead to an equilibrium state, so that the vapor and liquid phases will be at equilibrium after flash or partial condensation, and that will ensure the maximum possible separation of the components between the two phases. So in that way, we find that the partial condenser or partial reboiler can enhance the separation efficiency of a distillation column, so that they are also included in the counting of the stages. On the other hand, a total reboiler or total condenser will condense or evaporate the whole mass of the vapor or the liquid, so that there will not be any change in the composition between the two phases before and after the condensation and evaporation. So they will not add to any separation, so they will not be counted as the stages in a overall distillation based separation. Now I am skipping some in between questions for which the answers can be found directly from your lectures. I straight away go to some problems which maybe I can talk something about the stages, stages, because sometimes this particular thing is confused. What is stage? Stage is a one device or more than one device that will basically try to mix up, cause mixing of the two phases, that is liquid and vapor phase, and then what will happen in case of distillation, and then by this ensuring the mixing, some separation is obtained of the and then what happens that after this separation is obtained, then it is also necessary for us to see to it that we can disengage the two phases to get the products. Okay. So in a stage we are first carrying out a mixing and then disengaging of the phases to have the products. Okay. So that is how we look at a stage. And ideally a stage will ensure that after the mixing of the two phases, the product phases will be at equilibrium with each other. Okay. So that way it becomes an ideal stage or an equilibrium stage. But if there is not proper mixing, because maybe that we are not able to provide enough time of mixing, then the two phases will not come to equilibrium, and so that the separation obtained will be less than the separation obtained by an ideal stage. Okay. So that way we say that the stage is a fraction of an ideal stage. So ideal stage is given as a unity value, whereas the real stage is given a value which is less than unity, that is less than 1 but more than 0. 0 means there is no separation at all. Okay, it may go to 0, but why should we have a stage which is having a 0 with no efficiency? Okay. So a real stage will be having a value which is less than 1 but generally more than 0. Then we come to assignment 4. In this assignment 4, first we see that we have asked you to find out the pressure drop in a pipeline when the natural gas is flowing. So here you have been given some data, and you know that the pressure drop depends on the type of flow we are getting, whether we have laminar flow, whether we have turbulent flow. And in this case, we first see that we find Reynolds number to ascertain what kind of flow it is, because the Reynolds number decides the value of the pressure drop, and depending on the value of the Reynolds number, we select the appropriate correlation to calculate the pressure drop. So in this case, what we find that this Reynolds number is coming to this particular value. This is much less than 2000, that is the critical Reynolds number in a pipe flow, a circular pipe flow. So we see that this is a laminar flow, and in laminar flow we take this Hagen-Purcell equation and we find out the pressure drop value. Okay. So this is how we are obtaining the value of the pressure drop per unit length. Okay. So next we come to another problem. This is similar to that. Here also we are finding the frictional head loss. Now this is frictional head loss is something like pressure drop. Only thing is the difference is this, that pressure drop is given in terms of the units of the pressure, whether the head loss, any kind of head loss is given in the units of length. Okay. So, and as you know that pressure and length are related by that factor rho g, density into the gravitational acceleration. So, that way if you have pressure, you can find out the corresponding head and vice versa. Okay. So, in this particular problem again we find that we have to give in terms of head. So, we write the convert the expression in terms of head and we get this kind of pressure drop in terms of the head, okay, some millimeters. Again the next problem is for two-phase flow, and here we have been asked to find out in which flow regime we have, and this is important because whenever you are transferring liquefied natural gas, then when it goes into pipeline, the pipeline is at very high temperature. Initially the liquid natural gas will first evaporate, and when it evaporates it will form two phases. Okay, and these two phases will be existing in the pipeline, and that will cause different type depending on the type of flow regime this two-phase flow shows. So, you will get different pressure drops, and this is important for us to know because depending on the pressure drop we shall be procuring the compressor, okay, and or the pump. So, this determines the pumping cost of the natural gas or the liquefied natural gas. So, that is why it is important for us to know what kind of flow regime and the pressure drop corresponding to that kind of flow regime. So, from this particular chart, if you plug in the values given in the particular problem, you can easily locate which regime, means you get this value which is given in the x-axis, you get the value which is given in the y-axis, and then you try to figure out in which domain, in the which region these two values are coming. So, from there you can very conveniently find out the type of flow regime. Okay. And then once in the flow regime, then you can use these correlations which were given in your lectures to find out the pressure drop, and you can see that with the kind of data you are given, it is coming to annular. What is annular? Annular flow regime means if you consider a pipeline that the wall of the pipeline will be covered by the liquid, okay, and there will be inner core through which the gas will pass. Okay. So, this is an annular flow. So, with the kind of data we obtained, we find that this is an annular flow, and corresponding to annular flow we again find out the pressure drop. Okay. Next question was on a manometer. A manometer, it is a device which can measure the pressure drop between two locations, and in the pipeline generally it is used, and you saw that there are two limbs. It is called U tube because it is a two limbs, and this takes a shape of the U, and in this particular manometer we have some manometric fluid, and this manometric fluid, it will be moving inside this manometer, and you will find that depending on the pressure difference across these two limbs, this fluid will be going to one of the limbs. Okay. And in this case, as you see that some air is flowing over here, and as air flows, there will be a pressure drop due to the frictions. Okay. The pressure drop as it moves along. So, due to which we will find that whatever is the upstream pressure, say P1, that will be more than the downstream pressure, that is P2, and this manometer is measuring this pressure drop, and you see that this particular height, from the, if you see this is a datum, then this you see that this height difference is telling us about the difference between these pressures P1 minus P2. So, this P1 minus P2 can be correlated very easily by a force balance, okay, and we find that we get the pressure drop in terms of this height. And here in this case we are in this particular example we are neglecting the effect of air density with respect to the density of this manometric fluid, and this is, in this case it is mercury. So, mercury has much higher density, about 13,600 kg per meter cube, okay, and whereas air may be taken to be around 1 kg per meter cube. So, because of this high difference in the densities, we neglect the effect of the air density and get this particular expression to find out the pressure drop. And then the next question was on the quality determination. Quality means that how much liquid or how much vapor is present in a two-phase mixture. So, in this case also you have to basically go back to your lecture notes, and there were some tables and some formulas were given. So, these kind of tables you will find out. So, all these things you will find out, and using some appropriate formula which was given, you can find out this value which was asked in your in this question, that estimate quality in GP, that is gallons per hour. So, to find gallons per hour you will be using this particular equation, and then all these parameter values will be taken from some table, FB, FR, FG, from some table, and ultimately you will find that you will be finding out the value of this particular Q, okay, in terms of GPH. Okay, so these are quite straightforward problems which just kind of gives you from practice how to look into the tables and determine these values. Okay. The next question was on some temperature sensing device. In this case, it is the platinum resistance thermometer. And here you know that these kind of thermometers have to be calibrated, and these thermometers give they have some resistance, and this resistance is measured with change in the temperature. So, this resistance is correlated with the temperature, and these correlations are obtained by carrying out experiment and by regression. So, which in this particular problem we find that for the correlation this calendar Van Dusen equation was used, and in this particular equation these are the coefficients which are there, and so you have to simply plug in the values of the coefficients. So, as you see that this is the equation which is given to correlate the temperature with the resistance, and you put these values of the resistances, and because here the thing is this, that you cannot find the value of the temperature directly, you have to go with iterations with the kind of equation you are dealing with. Here is the Van Dusen equation. Okay. Now, you see that you have been asked to find out temperature. So, but you have been asked given the value of the resistance, and because this is a nonlinear equation, nonlinear algebraic equation. So, because of this you cannot, and that too it's cubic. So, had it been parabolic, you could have analytically solved for it, but as soon as it goes beyond second degree polynomial, then it becomes difficult for us to get an analytical solution. So, we have to go by some iterative method, and here in this particular thing you see that an iteration has been shown, that how you can iterate over it. First, you assume it to be linear, that means you take out the nonlinear terms, that is in terms of t square and t cube. So, you first solve for linear term, that temperature you can get very easily, and after getting this temperature term, you then you take this temperature value, plug in the values over in this, again in this equation. You just rearrange the equation a bit here, as you can see it is rearranged, and then you basically what we do that with this, what this was first this iteration, this value, what you do that you again take this value and on this right hand side and again find out the value from the left hand side. Okay. So, it is simply you can, this is one of the ways which have been shown to you to find out temperature. You can adopt any suitable numerical technique to find out the value of the temperature. Okay. So, you see that many iterations have been done to arrive at the right value of the temperature from the measurement of the resistance. And here is a question that is on the steady state conductive flux, and again you know that they are very standard problems which have been given. This kind of equations are used, that is the Fourier law of conduction, and we are using that, and here we find that all the temperature differences have been given, and this is how you are able to get the flux value using the Fourier's law of heat conduction. So, these are quite simple problems where you just need small equations, and you will find that the values which are required for solving those equations will be given in your question. Only thing is this, you need to have some idea of the numerical techniques, because sometimes whenever you are dealing with some polynomial equation, you need to use some numerical technique to get the solution. So that's the only thing. Otherwise, you will find that most of these problems are based on basically plugging in the values to solve some equation. Okay. So these are some problems on the heat exchanger, shell and tube heat exchanger. In this case, only again you find that we have these energy balances. So we first go with the energy balance. If you have some specific problem, let me tell you that if you have some specific problem in understanding the solution, you can always get back to me through the forum so that I can explain any of the steps or any of the concepts which have been used in the solution. Okay. So I am just quickly going through the solutions which you will be also getting from our side. So if you just go through these, and all these equations were given to you in the lecture, you have to choose the appropriate equations, and you see that if you follow this solution methodology, you will find they were quite straightforward. Okay. And ultimately you get the area needed for the heat exchange. And this next problem is also very straightforward, and only thing is this: here you are asked to find out the value of the NTU, and from NTU you can find the effectiveness of the heat exchanger. Okay. So I am not going to detail of this problem because as I told you that it is basically plugging in some values from into the formula. So just go through it one by one, step by step. You should be able to get the answer and understand the concepts. Next, I go to assignment 3. In the assignment 3, as you see that here you have been given the expression for the EMF, okay, in terms of the temperature, and this is for thermocouple. See, for thermocouple we are measuring the EMF. Okay. So it is something similar to the one we just saw for the platinum resistance thermometer. There it was given in terms of resistance and temperature. Here it is with EMF and temperature, and the coefficient values have been prescribed here, and the temperature is in Kelvin. Okay, EMF is in millivolt. So these things have to be carefully noted because each of these correlations are very much dependent on the units. Okay, these values will be changing if the units are changed. So you have been asked to find out the EMF and the temperature is this. So you can see that it is very straightforward solution. You simply put the values of temperature here, take the values of coefficients from this table to this equation, and you will get the value of the EMF. Okay. So one thing I must again tell you, don't get panic that if you are getting some negative answers. Negative answers are not wrong answers. Negative answers have their own interpretations. So don't get panicked if you have done it correctly, if you have checked it properly, then if you get some negative answers, it is perfectly okay. Okay. Now your next problem comes to the determination of Reynolds number. Since I am going back in the assignment, that means you will find that the problems may be getting easier for you because the Reynolds number concept again came in the in your subsequent assignments where you were trying to find out the pressure drop. Okay. So this determination of Reynolds number was the foundation to find out the pressure drop in a pipeline. So here this particular problem have been asked to find out Reynolds number. Here you see that the density, viscosity have been given, and the pipe diameter through which the liquid, that is water, is flowing has been given, and also the velocity of water. So again, if you know velocity, you can simply use this particular formula for Reynolds number, plug in the values, you will get the Reynolds number value. Okay. And then the next question is about the physical significance of Reynolds number. You can go back to your lecture and figure out what is the physical significance of Reynolds number. In next problem is about the determination of the friction factor. Now you see the friction factor again depends on Reynolds number, and that means to do this problem you are asked basically to find out the Reynolds number and then choose an appropriate correlation which were given in your lecture to find out Reynolds number. So you see that here whatever data are needed to determine the Reynolds number have been given in the problem. Maybe there are some extra data to test you. So don't think that all the data given in the problem have to be used. Some data may be redundant. So you take the appropriate data which are required to find out the Reynolds number, and then once you have found Reynolds number, you choose the appropriate correlation in turbulent regime or laminar regime, what kind of geometry you have. Depending on that, you choose the appropriate correlation and find out the friction factor. So you see that here we are using a polyflow equation, and we are getting the friction factor value. Then it is about a theoretical question on RTD. You can simply go to your lecture notes, and next question is about something which is based on this particular table, which gives you the composition of a natural gas. So next, rest of the questions from 6 to 10 are based on this particular composition. You are asked to find out the average molecular mass, that is, that is the summation of the product of the this mole fraction and the molecular weight of the particular component. So that way you get the average molecular weight, and you see this is the formula you are using to get the average molecular weight of the particular natural gas. Then we have the specific gravity of the gas. If the molecular weight is this, again it is quite simple that we are told that specific gravity is something like this, that is the average molecular mass of the mixture divided by the molecular weight of the air, and here you have this value of the specific gravity. So you see that all these questions which have been solved here, they are also quite straightforward, and any kind of the more you practice all these problems, you will find that some of these concepts which are being taught to you through the assignments are quite basic level concepts. They not only help you in the natural gas processes, but these same concepts can be used for any other problem you face in the fluid mechanics or separation processes. So Reynolds number is used in fluid mechanics to find out the pressure drop. If you learn these concepts here, and we are recapitulating the concepts in these particular lectures, because so that you can again remember those problems, solve those problems, and can apply those concepts back into the natural gas. So all these problems which are being shown to you now in this particular thing are all very, very basic level problems which can help you to prepare for any other competitive examinations. Okay. So you will find some variations in these problems only. So just do the assignment problems properly, thoroughly, and I'm pretty sure that you will be able to get good foundation knowledge on this particular subject. Okay, not only in natural gas, but also something to do with fluid mechanics, something to do with heat transfer, something to do with the measurement techniques. Okay, all these things. That is how I have chosen the assignment problems for you, so that you can prepare yourself for various types of competitive examination. Now next we come that heating value of the gas. In this case you find that heating value is found from this particular heating value, and you have been asked to find out the Vob number. Okay, so Vob number, as you know, that Vob number is found from the high heating value of the natural gas with this particular formula. So please understand that because this whole 6 to 10 this problem 6 to 10 are kind of together, the bunch of problems. So you will find that many of the data you will be taking from the previous problem. Okay, so nothing new in this, you just have to take the data from previous problem. So you see that if you are doing them in serial manner, you should not be able to find that you do not have some data missing, provided you do it serially. But if you choose randomly, then you may find that some data are missing. Okay, so I would suggest you to go to do these problems in the same sequence as they have been given to you. Okay, so you've seen that it is very easy to find out the Vob number, provided you have solved the previous problems or interconnected problems. Similarly, here you have the value of the CARI value, and here again you, as we have said, see we are writing that from question 7 we are writing. So again you see the CARI formula, and you have been given this A by F ratio, and this value have been found from the previous problem, so that you are able to get the value of the CARI. So, that way I find that this particular table was missing and for some reason, but now this table has been provided to you also to solve these problems. Next we come to the problem set 2, and here we find that again this is a very basic level question have been asked, that for a mixture the equilibrium constant is not a function. So, not a function of which one? So, you see that equilibrium constant is a function of the temperature, pressure, density and species concentration. These things are given, but density does not affect the equilibrium constant. Okay, it is a species composition which the composition of the phase or the temperature, pressure, but density never comes into picture in the equilibrium constant. Okay, because it is basically this is the volatility which matters. Okay, volatility or solubility, these kind of things, not the density. Okay, density does not appear explicitly. It may be affecting the volatility or the solubility in an indirect fashion, but it never comes directly into the picture. Okay, and then we have this for non-ideal solutions. How do you assess the vapor liquid equilibrium process? And here we have seen that the activity coefficient is used, and this activity coefficient is generally a function of the temperature, the pressure and the composition of the liquid, but it is not a function of the volume. So, that means it is not a function of volume, rest it is function of the liquid composition, the pressure and the temperature. Similarly, for fugacity coefficient generally used for the vapor phase. Okay, and in that case it is find that fugacity coefficient, if you go to thermodynamics, it is a very general term. It can be applied for liquid, it may be applied for the vapor. Okay, I am not going into detail of these thermodynamics because that is not the focus of this particular course, but just telling you a bit of it. So, in general, this fugacity coefficient is also a composition dependent, other than besides the temperature, pressure, it is a composition dependent parameter. Okay, but it does not depend on the partial pressure. Okay, and then this particular problem is about degrees of freedom, and is a very important concept in this. As you know that degrees of freedom is the minimum number of intensive variables that have to be specified to describe a system completely. Okay. So, in that respect you see that this particular problem is very important. In this kind of things, you have to first appropriately count the number of variables, and please understand generally if you see this particular thing that there is this F, V or L, they represent the flow rates, then Z, Y and X denote the compositions, then HF, HV, HL are the enthalpies, TF, TV, TL are the temperatures, PF, PV, PL are the pressures. Generally, we do not consider the enthalpies in counting the number of variables, because enthalpy is not a direct, it is a derived quantity. That means, if you know temperature, pressure, which is generally the case. Okay. So, if you know temperature, pressure, you can find out the value of the enthalpy. So, it is dependent. So, we do not count this particular variable. But even if you wrongly count it, suppose if you count it wrong, it's not a, that is, you are not going to get a wrong result. So, even if you count it, then just please make sure that you are also putting under the equations those equations which are correlating the enthalpy with the temperature, pressure. Okay. If you remember to do that, then even if you count the enthalpy, you will be getting the right value of the degrees of freedom. So, here we have shown how this counting has been done and how the variables were counted, how the equations were counted, and in this case you see that we are using the mesh, that is the mass balance, equilibrium, summation and then enthalpy balance equations. So, all them are listed here and we are counting those things to get the value of the degrees of freedom. And then we also go for the Gibbs phase rule and that is that F is equal to C minus P plus 2. So, we use that particular formula for Gibbs phase rule, and we have to say that which are not correct for the Gibbs phase rule, please go back to your lecture so to answer this particular question. Okay. Then methane number, also you see your lecture notes to find out the methane number of hydrogen. It is 0, okay, and it is 100 for pure methane. And then see the definition of Bob number and its significance to answer this question on Bob number. Then this is the degrees of freedom. Again, go back to the previous problem, just previous problems here, whatever we have done for degrees of freedom here. So you can go back to previous problem and you can find out for the natural gas what it would be. Here you see that the components have been given, the state of the things have been given. You can find out the degrees of freedom easily. Okay. Now next is this particular equation has been given to you, and this problem 9 and 10 are based on this. That is Antoine equation, and it is very straightforward, very basic level question. Okay. So this here you have been asked to find out the vapor pressure at this particular temperature. You simply plug in the values over here. Just keep in mind that this temperature is in degree centigrade, so you don't need to convert it into Kelvin. Okay. So you put directly this value over here and you get the value of the vapor pressure in terms of the millimeter of mercury. Similarly, the last question is on the same equation you have to use, but it's for hexane. Okay, now in this case you have been asked to find out the saturation temperature at 1 atmosphere. So it is the other way around, that is you are given the pressure here. So you take this, that means for a given pressure you get the saturated temperature, and for a given temperature you want to get the saturated pressure. So in any of the two cases you can use this equation. Okay. So for hexane the pressure is given 1 atmosphere. So you plug in the value of 1 atmosphere in terms of mercury, millimeter of mercury, that is 760 mm of mercury. You put the value of 760 and just solve this equation. You can just get analytical solution of this equation and you can get easily the value of the temperature. Okay. So I think I have comprehensively today discussed the various assignment problems based on the inputs I get in the discussion forum, and just I hope that you have been able to grasp the basics or fundamentals of these problems, and these problems will help you if you go to these problems. Most of the problems you will find are quite general in nature and which you can apply in the other subjects. Okay. And I am pretty sure if you do these problems properly, if you develop the fundamentals, you will be able to do quite well in the various competitive exams you are going to face in future. So wish you all the very best. I hope that you are preparing for your exam and you have registered also in the for the examination that is going to be held on 28th of October. Okay. So keep preparing well, and I would like to have another live session with you in the coming month. I would like that you pose more and more questions to me so that I am better equipped to answer your questions, clarify your doubts during the live session. Okay. So with this I come to an end of this session. Have a nice time. Thank you.